Hello everyone, welcome again in my class. Today we will start module number 4. In last lecture, we talked about elliptically polarized light. The module 3 covered whole polarization. Yeah. Now, in today's class, we will be formally introduced to interference. Now, in this module 4, interference of light waves will be discussed, and then we will talk about interference of polarized light. There is a small application of polarization while discussing interference, and therefore, we covered polarization before interference. Then we will talk about the famous Young's double slit experiment. Then instead of using the coherent light sources, we will use white light and see how does it affect the fringe pattern of Young's double slit experiment. And then we will introduce a thin film we will cover one slit using a very thin transparent film, and then see the changes in the interference fringes, and we will try to calculate either refractive index or thickness of the film using Young's double slit experiment. And in the last, we will talk about Fresnel biprism. Okay. Now, today we will start formally with the interference of light waves. Okay, we know that when two waves superpose, one obtains an intensity distribution which is known as interference fringes. Yeah. Whenever we talk about fringes, we mean that there is a distribution of intensity. We launch two light, they superimpose, and they automatically create some pattern, and this is called fringe pattern. We see their maxima, minima. Okay, and this particular type of fringe pattern depends upon the wavelength of the light, it depends upon the frequency of the light, it also depends upon the type of the slits which we are using. Okay. For light waves, one cannot observe interference between the waves from two independent sources. Okay. This is the usual sentence which we learn in our textbook. Okay, but this is not the case. Usually whenever we say that the two waves are interfering, then we expect as a result of interference observation of fringe pattern, and whenever we see some kind of fringe pattern, we say that the two waves must have interfered. Okay. But this is not the case. The observation of the fringe pattern is for the sake of measurements, irrespective whether we are observing fringe pattern or not, the two waves always interfere. Okay. But usually at junior levels, we say that as long as the two sources are coherent, then only we observe interference. Okay. But the truth is that, or the reality is that, irrespective whether the sources are coherent or not, irrespective whether their frequencies are very closely placed or not, the waves will always interfere. Okay. But to observe sustained interference fringes, we require waves which are coherent and which have almost same frequencies, and the amplitudes are almost equal. Okay. These are conditions which are given because we want to observe beautiful fringes, because we want to observe sustained interference fringes. Okay. If the interfering waves are not coherent, the interference will happen there too, but the thus generated interference fringes will not be sustained. That is, the positions of maxima and minima will keep changing. Okay. And once the positions of maxima and minima are changing rapidly, then we will see a uniform illumination on the screen. Okay. Interference fringes are getting formed there, but it is inability of our instrument, inability of our eyes, which are not able to detect them, because their positions are rapidly changing. Yeah, but interference in any case is happening there. Okay, the phenomena does exist in all the cases. Okay. Now, having said that, to observe beautiful sustained interference fringes, we require a phase relationship between the two interfering wave. And what is this phase relationship? This phase relationship says that the phase difference between the two interfering wave must be constant. Okay. And if the phase difference is constant, these two waves are called coherent waves, and the interference pattern produced by these two interfering waves is very beautiful. You will see very bright maxima, dark minima, and their position do not alter with time. Okay. Now, optical interference corresponds to the interaction of two or more light waves yielding a resultant irradiance that deviates from the sum of the component irradiances. Okay. Suppose we have two sources which are emanating intensities I1 and I2 respectively, then after interference the resultant intensity will not be equal to I1 plus I2. Okay. We know that interference follows superposition principle, and what superposition principle says is that the amplitude of the two waves must be summed vectorially, not the intensity. And if we sum up the amplitudes, then to calculate intensity we will have to square them up, and if we square amplitude A1 plus A2, then there would be a cross term also. Okay. Therefore, I1 will never be equal to I1 plus I2. Okay. Now, according to the superposition principle, the resultant electric field intensity E, now we are talking about field, that is intensity, amplitude. Yeah. The resultant electric field intensity at a point in space arising from the separated field, it should not be intensity here in this area. The resultant electric field E at a point in space arising from the separated fields E1, E2 and so on of various contributing source is given by E is equal to E1 plus E2 plus dash 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 dash. This is the statement of superposition principle. If we have n number of sources which are emanating E1, E2, E3 and so on fields, then the resultant field would be vector sum of all the contributing fields, and this is what exactly being done here. Okay. The resultant field E is equal to vector sum of E1 plus E2 plus E3 and so on. Okay. The optical disturbance E varies in time at exceedingly rapid rate. Yeah, we know that the frequency of optical wave is around 10 to the power 14 hertz, which is a very big number. Therefore, E varies very rapidly and it is extremely difficult to detect E. Yeah, and this makes the actual field an impractical quantity to detect. Yeah, we require very dedicated experimental facilities to detect it. Then what is easy rather is to detect their intensity. Yeah, therefore, the irradiance or intensity is measured directly. Okay. Then people may ask what is irradiance? It is nothing but it is synonyms of intensity, and how it is defined? Irradiance is defined as time averaged Poynting vector. Okay. This S is nothing but Poynting vector. Okay, which people study in electromagnetic theory. Yeah. Then if you take the time average of Poynting vector, then we get irradiance or intensity. Yeah. which is equivalently which we can write equivalently as C by mu naught time average field square, and which is equivalent to C into epsilon naught time average of E square. Yeah, B is your magnetic field and E is your electric field vector. Yeah, if we take time average of E and B field, then from there too we can calculate irradiance. Okay. Now, here C is the speed of light in vacuum, and epsilon naught and mu naught, they are permittivities and permeabilities in vacuum respectively. Yeah, epsilon naught is permittivity in vacuum and mu naught is permeability in vacuum. Now, these quantities are defined in vacuum. How would the irradiance be defined in a medium where n is not equal to 1? Now, in a medium, irradiance is defined by this relation, where epsilon is medium permittivity, v is the velocity of light in that particular medium, and E is the electric field, and we took here the time average of E square. Okay, this is how the intensity or irradiance is defined in a medium. But whenever we calculate irradiance in our derivations or while calculating the maxima and minima, we will always be concerned with the ratio of the intensities. We will always be concerned in relative irradiance. Okay. And whenever we will take ratio of two irradiances, the constant which appears before time average E square, which are epsilon into V, they will go away. Therefore, from now on, whenever we express irradiance, we will neglect epsilon into V term. These coefficients, these constants would be neglected here on, okay, because we would be calculating the relative irradiances in the same medium. Okay. Therefore, we will define irradiance I as time average of E square. Okay, is a vector quantity. E is our electric field vector. Now, having said this, now consider we have 2 point sources which are designated by S1 and S2. Okay. Since the S1 and S2 are point sources, they will emanate spherical wave fronts. Yeah. The shape of the wave front would be spherical. Now, suppose we have a point P which is very far from these two sources, and distance of P from S1 and S2 is such that by the time these spherical wave fronts reach to point P, they almost become plane. Okay. The P is so situated in at such a distance from S1 and S2 that the spherical wave fronts which get emanated from point sources S1 and S2, they can easily be treated as plane wave when they reach at point P. Okay. This is what exactly is written here. The point of observation P far enough away from the sources so that at P the wave fronts will be plane. Okay. Now, we also consider that point sources S1 and S2, they emit linearly polarized wave. Okay. Now, we will analyze this situation mathematically. Okay. Suppose E1 is the field which is emanating from point source A1, and E2 is the field which is emanating from point source S2. Then E1 can be expressed as E naught 1 cos k1 dot r minus omega t plus epsilon 1, where epsilon 1 is the initial phase, k1 is the wave vector associated with S1, and r is the radial vector. Okay. Similarly, for E2 we have this expression, and they both are given by equation number 1. Okay. Now, this quantity you see it is a dot product K1 dot R, and therefore, it is a, since it is a dot product, the resultant would be a number, a constant. Okay. K1 is the direction of the wave vector and R is the radial vector. Now, the resultant would be a scalar, and therefore, we can easily, it is a dimensionless quantity, and we can easily take the cosine of this number. Now, if we want to calculate the resultant disturbance at point P, the point of observation P, then what we will have to do? We will have to sum E1 and E2 and then square this expression, and the resultant will give the total disturbance or total irradiance at point P. Okay. And this is what is shown in this expression. The resultant irradiance I would be time average of E square, where E is E1 plus E2. And how to calculate E square? To calculate E square, we take dot product between the two vectors E dot E. Yeah, and what is E? E is equal to E1 plus E2. It is the resultant disturbance. Yeah. Now, after multiplying, we get this expression. The resultant field at point of observation P would be equal to square root of E1 square plus E2 square plus 2 E1 dot E2. Okay. Now, you see here, this is the irradiance due to the first source, this is the second term is irradiance due to the second source, but apart from these two contribution, we have a third term also, an extra contribution which owes its origin in multiplication between E1 and E2, and therefore, this is called interference term. Okay. Now, let us express, let us take time average of equation number 2 to calculate irradiance. Yeah. When we take time average, then we express the time average of E1 square by I1, time average of Et square by I2, and time average of this cross term by I12, and therefore, the final expression takes this form. The resultant irradiance I will be equal to I1 plus I2 plus I12, the cross term. As said earlier, I12 denotes interference term. Okay. Therefore, the resultant would not be equal to the sum of magnitudes of the two interfering wave. There would be, at few places the magnitude will go up, at few places the magnitude will go down, at few places it may go to 0. Yeah, we will analyze these things slowly. Now, the time average of E1 square we know. Yeah, we know the expression of E1, we can calculate the time average of E1 square. Similarly, we can calculate the time average of E2 square and the time average of E1 dot E2. Yeah, but this is a interesting part. Yeah, I12 is interference term. Let us see what are the quantities on which I12 depends on. Okay. To calculate the expression for I12, let us first calculate the dot product between E1 vector E1 and vector E2. We just substituted the expression for E1 E2 here, and then we got this big expression. Okay. And here again the cosine function is expanded in using the formula cos A plus B, and after this expansion we get expression 5. Now, once these things are done, let us take time average. Then the question arises, what is time average? The time average of a function f t over an interval t is defined through this relation. Time average of f t is equal to 1 by t integral of f t prime with respect to d t prime within the limit small t to small t plus capital T. Okay, where period tau of the harmonic function is given by 2 pi by omega, where it is assumed that tau is the period of f, which is a harmonic function, and this period must be much smaller than capital T. Okay, the interval over which the function is being integrated, this interval must be much larger than the period of the harmonic function. Okay. Once these criteria are met, we can easily take the time average. So, after taking the time average, we get this expression. Okay. The time average of E1 dot E2 is expressed here by equation number 7. And how did we calculate it? While taking time average of cos square omega t, we substituted it with half. Similarly, the time average of sin square omega t is equal to half, and time average of cross term which is cos omega t into sin omega t, this is equal to 0. Yeah, this we can easily do. It is a simple integration. Therefore, the resultant interference term, which is half of time average of E1 dot E2 is equal to E1 dot E01 dot E02 into cosine delta, where delta is the phase difference. Yeah, this is from first wave, and the second term this K2 R plus epsilon 2, this is from the second term, second wave. Yeah, we started with two waves E1 and E2, and this belong to first wave, while this belong to second wave, and we are taking difference here between the two. This means this del, which is appearing in equation number 8, it is a phase difference. Okay. And this is what is written here, del is equal to K1 dot R plus epsilon 1 minus K2 dot R minus epsilon 2, and this is defined as phase difference arising from the combined path length and initial phase angle differences. Yeah. If you rewrite this expression of delta, then you get this, delta is equal to K1 dot R minus K2 dot R, one bracket, and then plus epsilon 1 minus epsilon 2. This term, this is the phase difference arising out of initial phases. Yeah, epsilon 1 is the initial phase of wave 1, epsilon 2 is the initial phase of wave 2, and therefore, epsilon 1 minus epsilon 2 is phase difference arising out of initial phases. Similarly, K1 dot R minus K2 dot R stands for phase difference arising out of path length difference. We have already defined what a path length is. K1 is the wave vector, R is the radial coordinate of the point to which the wave is travelling, then K1 dot R is the path length travelled by first wave. Similarly, K2 dot R is the path length travelled by the second wave. The difference is path length difference between the two waves. Okay, and this also contribute to a phase difference. Therefore, we can say that the resultant expression of phase difference has two components, one correspond to path length difference and the second correspond to initial phase angle difference or initial phase difference. Okay. Now, again come back to the expression, final expression of interference term. Now, here you see the first term is vector E naught 1 and the second term is vector E naught 2, and between the two we have kept a dot. We are taking dot product between two vectors. E naught 1 and E naught 2 are the amplitudes of the two waves, and the information of direction is also embedded in it. And what is the information of direction? The information of direction means the polarization information. The polarization information is embedded in these amplitudes. Okay. Now, we are taking the dot products between the two vectors. Okay. Therefore, polarization also comes into the picture. Polarization is associated with E naught 1 in form of vector. Similarly, the polarization of wave 2 is associated in E naught 2 in form of a vector. Okay. Now, we are taking the dot product between these two vectors. Therefore, the relative orientation of these two polarization which are associated to the two waves will affects the output, will decide the value of I12, the interference term. Now, let us consider a special case. What is this special case? This special case is if E naught 1, vector E naught 1 and vector E naught 2 are oriented at 90 degree, then what would be the interference term? Okay. If E naught 1, vector E naught 1 and vector E naught 2 are perpendicular, then what will be the dot product? The dot product would be 0. E naught vector E naught 1 dot vector E naught 2, if they are oriented at 90 degree, they will give 0 value, and therefore, cross term or the interference term I12 would be 0. In this particular case, the resultant irradiance would be sum of irradiances of wave 1 and wave 2. Okay. But this is not the general expression. This expression is valid if the interfering waves are orthogonal to each other. The polarization is oriented at 90 degree. Okay. Hence, for two orthogonal polarization state, the flux density distribution will be unaltered. Okay. There would not be any alteration at the observation plane. The intensity would be uniformly distributed on the screen. We will not be able to see any kind of fringe pattern, because the intensity which we are observing at the screen is sum of the intensities of the two waves. Okay. Therefore, the resultant intensity would be higher than the individual intensities of the two sources or two waves which are falling on the screen, but there would not be any kind of fringe pattern. We cannot observe any fringe pattern there. It would be a uniform distribution of intensity. Okay. Now, let us consider a different case. Okay. Now, let us consider that the vector E naught 1 and vector E naught 2 are parallel, or they have the same linear polarization. Okay. To remind you, we started with the two waves which are linearly polarized. The first case which we discussed here is the cross polarization state, where the two polarization of the two waves are perpendicular. Now, in the second case, we are considering that the polarization are parallel, the two vectors are oriented at 0 degree now. Then what will happen? We will have maximum value out of the dot product now. Yeah, the interference term would be equal to now E naught 1 into E naught 2 into cos delta. Okay. Now, in this particular case, I1 would be time average of E1 square, which is equal to E naught 1 square by 2. Similarly, we can define what I2 is, which is time average of vector E2 square, which is again equal to magnitude of E naught 2 square by 2, and similarly we can define the interference term. Okay. Once these are known, then the total irradiance will have this expression. Okay. Once the cross term is known, we can easily calculate what is I1, what is I2. Okay. Once these are known, then we can express E naught 1 and E naught 2 in terms of I1, I2. What I mean is that I1 you can always express as E naught square in case of parallel polarization case, and similarly I2 you can express as E naught 2 square by 2 as is given here. And once you know this expression, you can substitute for E naught 1 and E naught 2 here, then you can express I12 in form of I1 and I2, which is given here. Once you know the expression of I1 and I2, the resultant irradiance now is given by equation number 9. Okay. In this resultant expression, where the polarization are parallel, you see that this is the first term which is I1, the second term is I2, and we have added term which is 2 square root of I1 I2 and then cos del. Okay. Cosine function means there would be some variation, sinusoidal variation. Okay. Sinusoidal variation means there would be a background intensity and this intensity would be modulated by a cos function. Okay. It means at some places on the screen we will have maxima, at some places on the screen we will have minima. Okay. And this would be periodic, there would be periodic variation in the intensity, and this is ensured by this interference term, the third term which is appearing here in equation number 9. Okay. While when the polarization were perpendicular, we saw that there were no fluctuation in the intensity at the screen. The intensity or irradiance at the screen were uniform earlier when two cross polarized light were interfering, but when the polarization is parallel, then we see a case where intensity is periodically varying, and therefore, it is forming of particular type of fringe pattern. Okay. Now, what would be the position of maxima? What are the conditions under which we will get maxima? These all depends upon the value of del, the phase difference. Okay. Now, what are the values which will give maxima? What are the values of del which will give maxima, minima? These are things we will analyze in our next class. Okay. This is the final expression which we obtained today, and I stop my lecture here. Yeah. In next class, we will move further from equation number 9, analyze it in for different values of del, and we will see what type of fringe pattern we get. Okay. Thank you all for listening me.